During this session, I think I'll keep the camera off so that
Yes, sir.
there is no breakage in the streaming.
Okay, sir. Now, good evening, participant and speaker. This is our first session of our FDP. Let me first give the brief introduction of Professor Dave. I say brief because if I give you complete introduction, that it may take more than 1 hour. So that's why I said a brief introduction. Dr. Harshit Dave sir is a professor in SVNIT Surat. He has completed his PhD from same institute. He has a more than 17 years teaching experience, more than 11 national and international projects he has dealt with from different sponsoring agencies. Apart from this, he has a 7th patent in his credit. He has published more than 60 international and national publications in journal, more than 100 conference papers. He has written 3 books with international edition and 6 book chapter in international edition. Apart from this, at institute level as well as in other organizations, he has served with various administrative positions academically as administrative point of view. Apart from this, let me give some informal introduction also. Supported us a lot to right from the beginning of this arranging this FDP, right from the proposal stage itself. So I would like to thank specially for that to Dr. Dave sir. And now I would like to hand over the sessions to Dr. Harshit Dave sir. Thank you very much, sir.
And I also welcome Dr. H.K. Dave sir specifically.
Thank you, sir.
I'm
Thank you,
waiting
sir.
for your introduction to over, and I formally welcome you because you have not remained
you very
present
much.
in our inauguration, but you were silently present. So again, welcome, sir.
Thank you. Thank you very much. Thanks for
Okay.
inviting me and giving me chance to speak to the participants of this program.
Yes, sir. Yes, sir. Please start.
Sir, is the presentation visible in full screen mode?
Yes, sir. Visible.
Okay, sir.
Yes, sir. Yes.
So formally, thank you very much, Piyush sir, for inviting me to speak to the participants of this program. I equally thank the principal of GC Dahod for his kind words. And yes, especially I would like to say that when we are sailing in the same boat, we always like and we always try to help each other. It is your humbleness that you are sharing credit with me also as part of this program. But the efforts that your entire team across different institutes that you have put up and the remarkable example that you are setting, that training programs can also be organized through the involvement of different institutes at a time. So that is praiseworthy, and I congratulate you in advance for a successful ATAL training program. I hope this would not be a single program, and Just as you have been conducting different other training programs, many more ATAL programs will come in future also, and that is how we will get chance to interact with each other. So having said that, as this is the first session of the training program, the recent developments in micro and nano machining in the context of Industry 4.0. So I would briefly like to talk about the micro machining process and nano machining process. Nano machining as such is in infancy, so I'll focus more on nano manufacturing rather than the machining part. Now, when we start this discussion, I assume that many of your participants would be coming from different parts of India. Just to give a brief idea about my institute, SVNIT is situated in Surat on the western coast, and it is one of the fastest growing cities in Asia. Very well known for its diamond and textile industries. Over and above that, the heavy engineering industries are also making remarkable contribution to the growth of our nation. Our institute is one of the National Institute of Technology set up in 1961 as Regional Engineering College. Right now, it is declared as Institute of National Importance by the Parliament of India. We run about 11 BTech courses, 20 MTech courses, 3 MSc courses, and recently we have launched an MBA program. We have more than 6,000 residential students on our campus, which is situated in the center of Surat. My department was established along with the institute in 1961, and we are offering BTech program with 240 sanctioned intake per year. We also run 5 MTech programs, one PhD program in almost all streams of engineering. And we are also starting executive MTech program from this academic year. We have 55 faculty members spanning in the age of 28 to 60. And we have 1,300 plus students in the department, wherein we have about 100 students coming from different countries across the globe. The major contents which I am planning to discuss is to initiate with the miniaturization, and from miniaturization, how we move towards micro manufacturing and then to micro machining. How we move from micro to nano technologies, that is what I wish to discuss. And finally, I'll conclude with some brief about nano manufacturing. To begin with, to give the idea about the micro and nano features. Generally, we as humans, we are able to see something which is in the range of say 1 mm. So we are able to see individual stapler pin if it is fallen on the floor. We are able to see the ants that are moving on the corners of our room. So some dimension which is around 1 mm is easily visible to human eyes. But once we start moving below 1 mm, we start entering into the micro domain. And if you see the blue mark over here, if you see this blue mark over here, this mark indicates the range where we can use microscopes which utilize some form of light so that the surface is illuminated and is visible to us. That range goes somewhere close to slightly lower than 1 micron, somewhere around 1 micron. So 1 micron, 1 mm is 1000 is 1000 microns. So when we go to 1 micron, we are talking about 1,000th part of an mm. Now beyond that, there is electron microscopy where the electrons are bombarded, and when they are reflected, they display the surface characteristics. So this electron microscopy starts somewhere around 10 microns, and it goes beyond 1 nanometer, below 1 nanometer. So the entire nano range, 1 micron is 1000 nanometers. So from 1000 nanometers to 1 nanometer, that entire spectrum is covered by electron microscopy. So the thing is, this range from 1 nanometer to 1 meter is something which we humans are right now focusing on. If we compare this size and scale, the ant that we see is somewhere around the size of 5 mm. And if you compare it with the manufactured parts, the head of a pin, this pin head would be about 2 mm. So this is slightly smaller than an ant. Similarly, the fly ash that we see would be in the range of 20 microns. And the human hair is in the range of somewhere around 100 microns. So if we compare it, we see MEMS devices, which range from these devices are in the range of 10 to 100 mm. But their intricate parts are less than 100 microns. Similarly, if we see the structures that come up, and right from those structures which we create, if we go to carbon nanotube, that carbon nanotube dimension is in the range of 1 to 1.5 nanometers. This is fabricated by certain manufacturing techniques, and this is comparable with the size of a DNA. So DNA size ranges from 2 to 3 nanometers. So I'm just trying to give the scale of dimensions, and if you can make out, the largest thing in this particular slide is an ant. So we are trying to work, we are trying to carry out manufacturing, we are trying to carry out the task in the range where the dimensions are almost non-visible. Now, if I compare this with dimensional magnitude, if I compare from 1 mm, if I go up to say 1 angstrom, we have a wide variety of manufacturing processes which undergo. So 1 mm, if I say conventional machining has a depth of cut we set is usually 1.5 mm. Once we start below 1 mm and go to 100 microns or say 10 microns, that is the range where micro drilling and micro EDM is being carried out. When I say this, I also wish to explain that when drilling can be carried out, it is understood that turning and milling are also carried out. So as we move beyond the micron range and come close to 1 micron, we start entering into the optical lithography. So where lithography is a deposition process which happens with the help of certain lights. And this light usually is a visible light. When we try to go below 1 micron, say 100 nanometers, we sometimes need to utilize the light in form of ultra UV rays. And this is the range where diamond turning is a process which is carried out. So today there is a possibility that we can have a machine which would have a depth of cut of 100 nanometers. So that possibility comes with diamond turning process. So by and large, these are the different ranges of micro and nano machining. And once we move close to nano machining, or if we try to go below it, wherein we work at an atomic level, I'll conclude my discussion with such an interesting example wherein atoms are replaced from one place to other. So some maybe you lift a pen from from your table and place it on the other side of the table. The same way you lift an atom and place it somewhere. So that sort of deposition is carried out wherein the atomic size itself is less than 1 nanometer. It goes into angstrom range. So that is also something which is possible in laboratories once in say 1,000 experiments. But yes, that is a possibility which has been demonstrated by the researchers. So to start with our discussion, the first thing is miniaturization. What is miniaturization? When we try to convert something to a smaller scale, when we want to scale down something, that is termed as miniaturization. So this is a new trend, miniaturizing, minimizing, reducing the size of devices and systems has started since last, say, 40, 50 years, 4 or 5 decades, this has started. And it is becoming more and more relevant today. So attempts are being made by various industries and various researchers to try to make things which are more and more smaller in mechanical or in optical or in electronic applications. So you can see some of those things I'm trying to show. This is a chip which is held by a plucker. This plucker is used to pluck by doctors to plug some of the impurities that go into our any sort of brushes that happen on our skin. So to remove that, this is the plucker that is used, and you can see how small the entire chip is. This is a lathe machine which is placed on your palm. So just you can assume the size. Drones we have seen, but if there is a drone which can be held in our palm, then that is something which is very small. And this is something which is like an encyclopedia. It has the details of all Encyclopedia Britannica, all 30 versions. And this is that single size of a chip which holds such large information. So miniaturization started sometime in early 1950s when computers were devised. But if you know the historical perspective, then you might be knowing that initially there were mainframe computers, and there used to be one in the entire industry. From that situation, this started reducing as workstations, as desktop PCs, and then it reduced to the size of laptops, and then palm tops came. Now we have smartphones, and there are discussions that these smartphones would also be eliminated in coming years. And this entire system may be in our specs or maybe on our wristwatch, and eventually it will go into certain sensors which may be part of our regular devices, or it can be fitted with the human sensory organs too. So we observe that the size of these products from 1950 to present days have drastically reduced. At the same time, the cost that is associated with it is also reduced from, say, millions to hundreds. That is how this has reduced. And at the same time, their numbers have remarkably increased. As per the recent data, there would be around 1 billion, 1.2 billion smartphones in India itself. And in the last year, Apple itself made about 4.7 thousand US dollars profit from India only. So that is the number of devices that are getting installed, all thanks to miniaturization process. Now, when we carry out miniaturization, we try to focus on two things. One is we try to create micro devices. Micro devices. So these are micro devices, they are microstructures wherein it is possible for us to actuate or carry out some transduction effect, or maybe carry out some chemical reaction, but with that some sort of actuation happens. So you can see two of these examples. These are being utilized in our mobile for certain applications. Now, multiple such micro devices, when they are integrated together, some devices for sensing, some devices for actuation, some devices for analysis, some devices for signals, and those devices, when they combine together to create a entire total system, then such systems are termed as microsystems. So in a way, what we try to do is, when we go for miniaturization, devices become micro devices, and the combination of various devices results into systems, and these systems become microsystems. Now, when we talk about miniaturization and their production, that entire branch is termed as micro manufacturing. And this micro manufacturing is broadly divided into two categories. One is the MEMS technology and the other is non-MEMS technology. MEMS technology is silicon-based technology. Usually it results into photolithography, chemical etching, LIGA, and other processes. This is not part of our discussion, so I'll not go into too much of these details. And the other are non-MEMS technology. Non-MEMS means I don't use lithography, I don't use chemical etching, I don't use LIGA, I don't use silicon as my raw material. Such processes are largely termed as machining processes. So these are those technologies which have very wide variety of raw materials and geometries and devices which are being created. And there we use micro machining, laser cutting, microforming, and other processes. So out of many non-MEMS technology, our focus of discussion is largely confined to micro machining. So with this micro activities, there is a scope to develop new innovative and high performance materials, develop new technologies and sophisticated devices. And at the same time, at research level, it is possible to compare and find the advantages of mechanics of miniaturized systems. However, there are issues. We are able to take a depth of cut of say half mm. If I want to which is fixtures becomes an issue. Now, when we are working at a depth of cut of say 100 microns, the tolerance range goes below 10 microns. So measuring those tolerance is an issue. Sometimes an issue. There is a sort of weak bonds between different parts, and because of surface tension and other activities, the parts may stick and may not result into the right set of form or geometrical accuracy. And residual stresses to the functionality. These are certain issues which are required to be addressed. Come to micro machining, micro manufacturing. Here what we do is concept or the theory of miniaturization, when is converted into practical application, it results in fabrication. What is microfabrication? Fabrication of structures, parts, products that are smaller than one. So this is the definition of microfabrication, not micro machining. Microfabrication means when I try to make some structure, say a pillar or an array of pillars, or maybe a slot, or maybe a circular groove, whatever structure I create, or maybe I create a part like an IC, I create a micro pin, I create a micro Statue of Unity. So those things that we try to create, and if we term their size as less than 1 mm, then that process is microfabrication. So the dimension ranges from 1 micron to 999 microns. However, when we define micro machining, we do not put up a need that the part that I generate, the product that I generate, has to be in the micro dimension. When we talk about micro machining, we talk about a process where a very small microscopic amount of material is removed in order to achieve a better geometrical accuracy, which usually is not available. So when we combine two words, micro and machining, we understand that we want to carry out machining at micro level, that is removal of material at micro level. So our understanding goes that we want to make something which is in the size of microns, but in reality it is not so. In reality, we do not focus on the size of the part, the size of the product that I make, but what we do is we focus on the size of the feature that we are generating. So I may have a 10 mm, 1 centimeter size of a aluminum foil. But if I'm able to create slot over it, if I'm able to create a hole into it, whose dimension is within the micro range, then that is micro machining. That process is micro machining. I am creating a feature on a part which is larger than 1 mm. Still, it is known as micro machining. So what we understand with microfabrication is that we try to create a part which is less than 1 mm. But in case of micro machining, we try to create something whose dimension, whose feature, the feature that we are generating is less than 1 mm. Of course, the part can be larger than 1 mm. I hope this is clear. Now, when we classify this, we may carry out some sort of, now when I say micro manufacturing, it can be micro forming also. So a solid part is given a different shape. It can be micro extrusion also, right? So when I say micro manufacturing, I divide it into two categories, MEMS and non-MEMS. But when I go into non-MEMS, largely the majority of the processes are those where material is removed. Take micro grinding, punching, laser cutting, drilling, whatever you take, except this extrusion, embossing or molding. These all processes are the cutting processes. Now, when I talk about mechanical micro cutting, I focus on turning, milling, drilling processes, micro machining. Of course, micro EDM is something which is very widely utilized in market. So the research point of view, all processes are being investigated in micro domain. But when we go for actual application, it is micro turning and micro milling, which are widely used as micro machining process. And in the advanced processes, micro EDM is a process which is being widely used. So I'll focus my discussion on these three processes today. Now, when we try to have a brief comparison between MEMS based process and mechanical micro machining, the capability of mechanical micro machining is enormous. In case of MEMS, we only need to have silicon as our workpiece. But here we can use metals, alloys, polymers, composites, ceramics, almost all materials we can use. The geometry that we try to create in MEMS is a planar 2D drawing or 2D feature or 2.5D at max. Whereas in case of micro machining, we generate complex 3D features. Usually assembly is not required, or in some cases you carry out bonding. But in case of micro machining, we may go for fastening, we may go for welding or as well as bonding. So if I want to weld parts, if I want to fasten some parts, then just imagine what sort of smaller electrodes I would require into that welding process, or what small size of rivets or maybe screws I would require if I want to go for fastening. So this leads to assembly, leads to altogether a different branch of micro activities. The accuracy level is better in case of micro machining, wherein you can go up to 10 raised to -3 to 10 raised to -5. The size of the machine in MEMS is large, whereas here you can have large machine also and micro machines also. As far as production is concerned, MEMS has an edge. Production rate, MEMS has an edge. And there are many applications where 3D structures are required, where mechanical micro machining applications may be taken care of. Now, when I carry out micro machining, how do I carry out micro machining? So in general, there are two approaches. One is, say for example, on a conventional lathe machine, the least count that I can measure is 50 microns. Using the scale which is marked on the cross feed, I come to know that 50 microns is the minimum dimension that I can measure. Now, if I go to CNC machining, the same size of machine, maybe larger size of machine, there the capability is 1 micron. So we have a capability of measuring 1 micron at a time. So here in both the cases, what we did was we considered a machine with 50 micron accuracy. Then we considered a same type of machine, almost same size, but it has the capability of 1 micron. Now, if I can reduce, if I can convert this CNC machine wherein this least count of 1 micron can be made to say 500 microns or 200 microns or to 50 microns or to 10, less than 1 micron, then that becomes a tedious task. So what we try to do is, when we are not able to create features, of course, least count being 1 micron does not mean that I am able to create 1 micron. It means that if I'm able to create 90 microns, I'm also able to create 91 microns. After 90, it's not that I will create 100 microns only. I can create 91, 92, 93 microns also. So least count being 1 micron does not mean that I'm creating features of 1 micron. So there are two ways in which we can start working on mechanical micromachining. The first is we reduce the size of the process. We reduce the size of the machine. We reduce the size of the tools. We reduce the size of the entire equipment as a whole. So what we had is a large lathe machine. Now you convert it into a lathe machine which can be placed on your table, and further you work so that it can be placed on your palm. So what we do is we do not focus on the feature right now. We focus on creating a machine which goes into micro domain. So our task is we want to go for miniaturization of the machine. So in our next session, we will be having some practical aspects of a miniaturized micro machining setup. So there you would have an idea about how the conventional lathe or conventional CNC lathe machine is reduced as a tabletop machine. So what in the first approach we do is we try to uh, reduce the size of the machine and make smaller machines. So what happens is the features like machining dynamics, chatters, cutting forces, what existed at macro level, they are directly transferred to micro domain. So there, if I had say 100 newtons of cutting force being measured, I would measure 100 millinewtons now. If I was measuring some vibrations in the range of say 500 microns, now I would shift to 5 microns of vibrations. So the thing is, everything that you observe at macro level, you start observing at micro level when you reduce the size of the machine. Now, reducing the size of the machine is not that easy as we reduce the size of a drawing, a 3D model on a software. There are a lot of issues that are required to be faced, and I suppose Mr. Kalpak will discuss this in the next session. The other approach is not reducing the size of the machine, keeping the size same, but improving the capability of the machine. So what you do is instead of using a motor which rotates as at 5,000 RPM or say at 20,000 RPM, you use something which can rotate at 1 lakh RPM, something which can rotate at 3 lakh RPMs. So what you do is from the scaling of the size, we move to cutting mechanics. So our approach here would be more focusing on the working on the geometry of the tool rather than reducing the size of the tool. We'll try to make the rack angle or maybe clearance angle to such a precise level that it will be able to carry out the right set of machining at micro domain. We can work on the crystal orientation at crystal structure level will go. So the thing is we don't reduce the size of the machine, but we make it more capable. We make it run at higher RPMs. We make it utilize highly precise tools, maybe made from diamonds, and then we try to focus on the geometries in such a way that we may not require to reduce the size. So in case of this domain where the machine size is large, often we are not that concerned with the cutting force individually, but because of the geometry, how cutting force can be controlled, that is what we try to focus on. So there are two approaches. Both of approaches have been widely investigated. You will find at least 500 papers in both the approaches. But for micro domain, to use it for industry is a struggle where people are still trying to create setups which can do that. So by and large, the micro machining, if we are making something micro optics in terms of MEMS, or maybe miniaturizing the process, so miniaturizing the size of the machine, we are reducing the size of the tool, or we don't reduce the size, but we focus on ultra precision. So in any of these three activities wherein we focus on micro manufacturing, there are n number of scope of understanding, scope of research, scope of study, like applications. We can work on micro parts, micro features, or microstructures. We can work on process parameters, tool geometry, or material properties. We can focus on cutting force, temperature, stress distribution, strain rate, all those parameters we can focus on in different situations and compare them with macro performance. We may focus on surface finish. In case of macro size, our surface roughness value ranges from somewhere around 10 to 30 microns. So here we will try to reduce it less than 1 micron. Accuracy and repeatability is something that we can focus on, and residual stress is an important issue that we face. And we try to optimize the processes by using various optimization tools so that the process becomes predictable, so that the process becomes producible, and so that the process becomes productive. So this is an entire development plan wherein people can focus on different sort of studies. Now, what are the major features that we focus on? The uncut chip thickness. Uncut chip thickness is nothing but the depth of cut that we set. So in case of micro machining, the micro macro border is somewhere around 200 microns. Initially, I said that when we work in micro fabrication, we make a part which is less than 1 micron. But when we are working on features, any feature that we are focusing on, a slot or a groove or whatever it is, that comes into the micro domain. So right now the capability of the machines are such that even large, even conventional lathe machines are capable of going below half mm, below 500 microns. So now the feature generation is restricted to dimensions which are less than 200 microns. So the border between micro and macro size is somewhere around 200 microns right now. The capability of micro machines is such that they are able to produce 100 microns now. They don't need to focus on, say, 900 microns. So because of this, the uncut chip thickness or the depth of cut that we can take up will be less than 200 microns. At some point of time, I will discuss about the tool geometry and the positive and negative rectangle. There we will understand that when the border is 200 microns, our uncut chip thickness or the depth of cut would be in the range of somewhere less than half of it. So 10 to 90 microns is a widely accepted depth of cut for micro machining. As far as dimensional accuracy is concerned, we'll try to produce something less than 1000 microns. But if there are, because there are 3D features, so in those 3D features, we'll try to see that at least two of those dimensions are less than 1000 microns. So usually the range of accuracy is 1 upon 1000 to 1 upon 1 lakh mm. And the roughness value is usually less than 100 nanometers nowadays. So these are the features. Cutting tool geometry, usually when we go for the single point cutting tools, then we are largely free from the restriction of the tool size, because we need to take a depth of cut. We generally take depth of cut of 1 mm with a tool which is of the size of, by itself, the cutting edge is of 5 to 7 mm. So the reduction in the size of the tool may not be required for turning or say facing operation. But on the same lathe, on the same turning setup, if I want to create a groove, then the width of the tool should be in the range of the width of the groove that I want to create. So when it comes to milling and drilling, the tool diameters in both the cases, end mill cutter or twist drills, these diameters are also reduced in size from, say, 1000, less than 1000 microns and up to 25 microns. To some extent, for turning and facing operation, we are relieved from creating such cutting tools. Of course, we create single point cutting tools for using as for creating grooves, or maybe for creating slots, or maybe for creating teeth. So for them, we need to further reduce the size of these tools. To begin with, micro turning. Micro turning is an effective way where we produce micro cylindrical or rotational surface. If you can see this, this is a micro pin, and this micro pin would be around 1 mm. From here to here, this size is 1 mm. But because this is put up under microscope, so it appears to be very large. But this is the dimensional scale of 200 microns. So roughly this would be somewhere around 1 mm. And its diameter, which was measured, was 33 microns. Just remember that the diameter of our human hair ranges from 60 to 100 microns. So if you can cut that hair into two pieces, then also this would be smaller than that. So 33 micron, you can assume this is what precise size is achieved. So high aspect ratio is possible with such micro turning process. Of course, cutting force is a culprit over here, which can, when you are applying the tool over here, and if there is slightly more chatter into it, then the job may bend if it is ductile and may break if it is brittle. So usually micro turning is something which is possible by both our approaches, on a tabletop machine also, and as well as on a large machine uh, where the where the machining characteristics are made highly precise. Some of the database of geometric characteristics can be obtained from this data. We are able to generate rotational convex shape with large aspect ratio like micro shaft or micro pins. The size is reduced to, there are capabilities which are demonstrated wherein diameter as low as 5 micron is created. However, that is once in a while. But by and large, somewhere around 100 microns is a usual practice in micro turning process. Roughness value that is being achieved is 100 nanometers, 0.1 microns. Now, that is easily possible. This is one such example which was put up by Dr. Rahman from National University of Singapore in 2005, where they tried to create this micropin. This micropin is comparable with the graphite lead that we use in our clutch pencils. It is 0.5 mm. And the largest diameter on this particular pin, when put under microscope, appears this way. The largest diameter is 0.477, slightly less than 0.5 mm. So these are the different features. You can see the taper, you can see the groove, you can see the steps, turning and taper turning, and everything is shown, is demonstrated on this particular micro pin. This is the fabrication process. I'll not go into that detail right now. So what we can think of is this micro features which we generate by a micro turning process. You can see that micro screw is generated. You are creating threads over it. Micro coil is generated. Some slots are generated wherein a coil can be passed. And you can see this is the facing. This is the face. And on this face, a hole is drilled, and you can see this face groove. So this groove is also possible to generate, wherein you can assume that this scale shows 100 microns. So roughly this would be somewhere around 200 to 220 micron diameter. So such precise level is possible. One widely used photo for micro turning is this one, which appeared in a research paper in early 2000s. This, you can just try to see that here is this is the motor, a tiny motor that you have placed. Along with this motor, you have put up your small chuck, and this chuck has a workpiece over here. You can see this is slightly blurred, but here is the cutting tool, and this cutting tool is held into this, and this is how the process is carried out. Now, if I want to move this, there are grooves which are created over here. So it is possible that I can slightly shift or slightly vary the positional of the parts of this setup. Swiss type lathe. This is a Swiss lathe which is considered to be one of the earliest micro turning setups, which were made and available in Switzerland for making parts of wristwatches, gears of wristwatches. They were initially made with this process. This appears to be an interesting work. There are few videos available on YouTube for this process. Very many examples. Micro turning is widely used in automobiles, in electronics, in watchmaking, as well as in biomedical engineering applications. Some of these applications I will discuss during the course of our presentation. Nano Corporation has made different machines, MTS 1, 2, 3, and 4, where micro precise tabletop CNC machines. You can see that this is a common machine. You have this chuck, and this is the motor, and here is a brass job. You may have tools somewhere over here. and then you slightly revised it, made it in a different form. Instead of sliding the entire chuck this way, you would slide it the other way. Then here is a possibility wherein I can hold a job so that, or a small drill setup so that I can drill hole also, and there are possibility of multiple tools over here. So the thing is, slowly and slowly the sophistication in these machines have increased. This by and large holds the record wherein the smallest micro lathe was developed, wherein the length is 32 mm. 32 mm means slightly larger than 1 inch. So maybe somewhere slightly smaller than our index finger. Its width is 25 microns, exactly 1 inch, and similar dimensions. So somewhere around 1 to 1.5 inches is the total dimension. And this entire setup weighs just 100 grams. Who knows? I can hold it and place it in my pocket also. So this is an interesting work, probably one of the first work where the capability of micro turning was demonstrated. So you can see the micro shaft is generated, screw cutting is done, grooves are being attempted to make, the taper is being made. You can see the groove cutting. This is the facing on a part that is being done. So as early as in early 2000s, this was demonstrated. The process micro domain turning has various advantages, like this is cost effective and high dynamics. It has smart footprint and it is energy efficient. I'll not go into too much of these details of these advantages due to short of some time. However, there are many challenges. The achievable minimum diameter of the shaft, I can carry out turning, but what smallest diameter of a shaft I can generate? So it goes with what aspect ratio I want to have, what length of this shaft I want to generate, and with that particular length, what diameter I want to work on. So that goes with the magnitude of cutting force that would be encountered. Sometimes this may result into deflection. So that largely restricts the capability of the machine. Uh, the other thing is when we try to improve the product, compare the productivity of the micro turning with the turning, then certain mold based processes give you better outcome 3D structures than micro turning. So that is also an issue. And when we want to create features on biomaterials or maybe on hard alloys or maybe on ceramics, then micro machinability of these components, these parts, these materials is still a small challenge which requires to be focused on. The other process which I said, which is widely used, is micro milling. You can just see this part. Here it shows that 2 mm is the width. So this may be somewhere around, this entire feature may be somewhere around 2 to 3 mm. So in spite of this, this having the dimensions in 2 or 3 mm, the features that are being generated are into micro domain. So because of that, we observe that this can be termed as micro milling. Two of these features would be in micro domain. If you see over here, the second image, these are the grooves which are generated. Now, if you compare the grooves with these walls, the walls are smaller than the grooves. But the thing is, because this is milling process, this is not additive manufacturing. So we are not producing these walls, we are producing the grooves, and eventually these walls appear. And then there is an example wherein a single pillar, a square pillar is also generated. You can see that the dimension is somewhere around 50 microns on one of the side. So maybe 50 or 70 by 70 micron size of this pillar. And it appears that if we take this as the base, then probably this is somewhere around 1 or slightly more than 1 mm. So the thing is, there is a possibility of creating such micro features. Now, when we discussed about two approaches for micro machining, those two approaches are largely confined to micro turning. Here, when you want to create this feature, suppose you want to create this groove. So the end mill cutter should have diameter of this groove itself. So you will have to reduce the size of the tool. So once you reduce the size of the tool, your tool holder will also be reduced. Once your tool holder gets reduced, then your entire entire spindle size will also reduce. And when that reduces, so you will have to reduce the size of your chuck and then the size of your workpiece raw material. So the everything is in case of micro milling. This process becomes possible when you go for one of the two approaches wherein we reduce the size of the machine. So we may not have diamond milling machines like we have diamond turning setups. So there would be a possibility wherein the machine becomes a tabletop machine. So here we directly scale down to the conventional milling process to micro milling process. So this will again have similar kinematics with what the turning has. And there would be interaction between the cutting edge of a milling cutter and the workpiece, which will result into some form of shear or some form of compression. And that is how the micro to nano size of chips would be produced. And that is how the machining would take place. If we try to compare the geometric characteristics, here we can make convex as well as concave surfaces. In case of turning, only 3D convex surfaces are possible, whereas in case of milling, micro milling, 3D convex as well as convex shapes with high aspect ratios and very high geometric complexities are possible. As small as 50 micron size of slots are practically applicable. There are features where you create slots as small as 50 microns. So if the slot width is 50 microns, it means your end mill cutter will also have 50 micron size of the 50 micron diameter size. Similarly, the surface roughness on certain aluminum components have been observed to be less than 10 nanometers. That have been observed, that have been reported. So there is a possibility to generate a mirror surface image on certain non-ferrous alloys like aluminum. Now, what really happens during this process? This is one of the cutting edge, somewhat like a single point cutting tool. It applies to turning also. In case of macro scale, when we are working at macro scale, what we do is our uncut chip thickness would be half mm, it may be 1 mm. That is what is our uncut chip thickness or our depth of cut. But the nose radius that you have would be less than 200 microns. Nose radius is generally 0.2, so 200 microns. So as compared to that, the depth of cut and the uncut chip thickness is quite large. So when you see this being carried out, the shape, the geometry of the cutting tool itself acts as a negative rake angle. The nominal rake angle is the real rake angle on the tool. So that acts as the nominal rake angle acts as the real rake angle, and that results into smooth machining and chips are formed. Continuous chips may be formed if depending on the type of workpiece, and that is how the cutting would take place with half or 1 mm of depth of cut. But when we go into micro scale, what happens is we reduce our uncut chip thickness. And if you remember, the boundary is at 200 microns. So your depth of cut is less than 200 microns. Now, if I use the same tool, its nose radius is 200 microns. So this surface, now what we are doing is we are carrying out this at a micro domain, micro scale. So the tool remains same, but it becomes enlarged. The same tool, but this edge is still 200 microns only, 0.2 nose radius. But now what happens is the chip uncut chip thickness or the depth of cut is less than 200 microns. So what happens is now when the chip is trying to get generated, this nose radius itself acts as negative rake angle. You don't produce a tool with negative rake angle, but the shape itself becomes a negative rake angle for the tool. And so the machining becomes difficult. And so the cutting becomes difficult. So what we need to do is we need to reduce the size of this tool. And so when we define this, we need to restrict ourselves to minimum chip thickness. Depending on the size of the tool, I will have to define the minimum chip thickness that I would produce, or the uncut chip thickness that I'll define, or in a way the depth of cut that I would go for. Depth of cut or the uncut chip thickness or the chip thickness that I'm going to produce should never be less than the said nose radius, because if that is smaller than the nose radius, then what happens is the positive rake angle becomes negative rake angle. So that is the only major difference that comes from macro to micro domain. And if we can take care of it, if we reduce the tool geometry, if we take care of the tool geometry so that our 200 micron nose radius becomes 100 micron nose radius. So I can very easily take a depth of cut of 150 microns and can effectively carry out the process. If I want to take depth of cut of 100 microns, then here the nose radius has to be 90 microns or so. So the thing is, because we want to have more accuracy, because we want to go for smaller depth of cuts, size of the tool gets reduced in case of micro milling. That is what is the basis of why we go to the micro domains. So this is that part. Now, in case of milling, shape and geometry of micro tools is very important. And micro end mill cutters of 25 micron diameter are easily available in micro. Of course, they are very expensive. It would cost us few thousand rupees, but they are available. There are end mill cutters with 5 micron diameter size also. Just assume what would be the flute size when the diameter itself is 5 microns. But they are not that easily available. Special orders have to be placed and they are made specifically on demand. So when you reduce the diameter, the stiffness of the tool will reduce. It will become soft. It will result into deflection. It will, in most of the cases, we have tried with 300 micron size of end mill cutters, 200 size of end mill cutters. And during the first or second cut itself, we have seen that often the tool breaks. So premature tool breakage or tool failures occur when we are working into this domain. So having the tool, carrying out the process is the next level of problem. But the first level of problem is making of these end mill cutters and then using these end mill cutters for our application. Now that is something about micro milling. Now I come to a slightly different process wherein we don't use mechanical energy. We use a solid tool, but there is no contact between tool and workpiece, and that process is an EDM process. So now in micro machining, I want to talk about EDM as a micro machining process. Now, why it is possible, why people attempted not other micro machining, but EDM for micro machining? Because here already the machining is done without bringing tool and workpiece into contact. So cutting force is eliminated. Once you eliminate cutting forces, many of the other problems also cease to exist. Now the other thing is, how does the material get removed? Material gets removed by the flow of electrons. Now the electrons are in angstrom size. So there is a possibility. Of course, nano surfaces are not yet being generated, but there is a possibility that from micro we can further go to nano domain also. So as other advanced processes, EDM has the best potential of becoming a micro machining process. And so researchers attempted it. And maybe since last 25-30 years, there are widely used micro EDM setups, tabletop setups are available. And we have attempted working with 300 micron size of tungsten electrode for creating slots, for creating steps, for creating grooves, for creating holes. So those things we have tried to attempt, and it has given a substantially good insight into the process. Few of the publications have come about it. So now when I go to micro domain, what is the difference that I observe between a regular EDM process and a micro EDM setup? In regular EDM, we use RC relaxation circuit, but here we use RC single pulse discharge circuit. So at a time, my focus is to generate only a single pulse. I don't want to generate thousands of pulse in a second. My focus is to generate a single pulse. Once I generate a single pulse, of course, it would generate in 10 microns. One cycle is over. So I keep on conducting thousands of cycles at a time. In case of regular EDM process, the voltage range is from 30 to 300 volt, and the current ranges from 20 to 100 amperes. Of course, those machines have capability to have 5 or 3 amperes also. They have the capability to go up to 10 voltage also. But the usual range is 30 to 300 volt and 20 to 100 amperes. Now, when we go to micro EDM, there the value is ranging up to 100 volt and the current is less than 3 amperes. Not only 3 amperes or 2 amperes or 1 amperes, you use current in milliamperes also. So basically here what you do is you use the capability of a capacitor. How much energy a capacitor can discharge, you focus on that during a RC single pulse circuit. So rather than focusing on setting voltage or current, you focus on setting the capacitance. Of course, I'll not go into too much of that detail, which may not be possible to discuss in this brief time. In case of EDM, the pulse on time is user defined. I can set on time as 100 microsecond or 200 microsecond or 500 microsecond or 50 microseconds. But in micro EDM, you don't set pulse on time. Of course, some machines have that understanding. They give you an idea about how much would be the pulse on time. But depending on the initial voltage and the capacitance, certain pulse on time is defined by itself. So you lose one parameter for varying and a variable parameter for study. Inter-electrode gap between tool and workpiece in EDM is certain in the range of some tens of microns, 10 micron, 20 micron, 30 micron or so. Whereas in case of micro EDM, this inter-electrode gap is less than 5 microns, as small as 1 micron. The specific energy available in a single pulse is very high in EDM, whereas you reduce it in micro EDM. The surface finish ranges from 3 to 30 microns. Usually it is more than 10 microns. And in case of micro EDM, this is from 0.5 microns, that is 500 nanometers, to 0.05, that is 5 nanometers. So the capability of micro EDM in generating good surface finish is enormous. So this is the brief comparison. Process remains same, principle remains same, wherein there is a tool and workpiece and there is a spark which is generated between tool and workpiece. And when sufficiently charged cloud of electrons is generated, there would be big breakdown, and because of that breakdown, the electrons will travel to the workpiece and they would transfer their energy on the surface. And once they transfer the energy, the material would not only melt, but it would vaporize and a small cavity is generated. This keeps on repeating one after the other thousands of times in seconds. And that is how the process goes on. I'll not go into too much of this discussion because it is more or less same with what EDM is. But what I'm interested in is we don't focus only on die sinking EDM. When we work on EDM, there are two variants. One is a die sinking EDM. The tool moves along Z-axis and it creates its mirror image on the workpiece. If it is a circular tool, it will create a circular cavity. If it is a square tool, it will create a square cavity. And by chance, on the surface of this square tool, if I create emboss, say H over it, then it will create an H on this final surface also. So whatever is the shape, its mirror image is created by die sinking process. The other variation is wire cut EDM process. But when we go into micro domain, there are other possibilities, the different variations of the process which are possible. So just like micro EDM, wherein the tool creates an impression. So this is the shape of the tool. That impression is generated and that shape is generated. That is micro die sinking EDM, wherein we generate micro gears, micro injection molds, embossing and other things. Then the other variation is micro drilling EDM. So what you do is you use a micro electrode, but this electrode is rotated also. Along with the Z movement, it is rotated at high speed. So we are able to generate micro holes. I call it micro drilling? Because the aspect ratio of this particular setup is more than die sinking. In die sinking, if I'm getting an aspect ratio of 5, 7 or 10, here I might get an aspect ratio of 50. So here rotating tool will result into wobbling action of this dielectric fluid within, and that would result into the removal of material easily. Easily means it is a relative term. It's not that really easy. But where do you use it? You use it to create micro holes in inject nozzles. You want to create reverse EDM tool electrodes, so that you carry out with the help of micro drilling EDM. Reverse micro EDM. In case of reverse micro EDM, what happens is this is the tool. This black color that you see is a tool, and this tool has cavities into it. And what I'm doing is I'm using this cavity to generate pillars. So my intention in case of usual EDM process, the feature is generated by removing material. But here the feature is not generated by removing material, but feature is generated by removing the surrounding material. So you can see that this pillar is not generated by depositing, but it is created by removing the material around. And how that happens? By using this tool. So this is something like a circular plate, and therein where there are different holes, and these holes will generate pillars. So that is reverse micro EDM. Otherwise, it is not possible for us to create such micro pillars by any other strategy. So reverse micro EDM is something which comes as a handy tool to carry out this task. The next variation is a planetary micro EDM. In case of planetary micro EDM, what we do is, this is the top view. What we do is the tool not only rotates, but it revolves like a planet. So it travels along this path. And while traveling along this path, it creates a cavity which is larger than the size of the tool. So in a way, you are decoupling the size of the tool from the size of the cavity that you want to generate. Up till now, we are aware that whatever is the size and shape of the tool, its mirror image is generated. Here, we do not generate the mirror image. Here, what we do is we generate a larger size of cavity. Of course, this is largely meant for generating circular cavities. At our place, we have attempted to generate square cavities by planetary setup through two different funded research projects. That has been done successfully. You may refer some of our old research papers for that. But planetary micro EDM is also an interesting process. Just as we have wire EDM, we have micro wire EDM process also. So here what we do is we work on smaller features, on smaller size of cuts. Rather than cutting say 10-15 mm of length, we may cut 1 or 2 mm of length and create a feature by cutting that small size. So certain forming tools or stamping tools or spinning nozzles, they are made by micro wire EDM process. A small variation is micro electro discharge grinding. What you try to do is you use a tool. This is the tool. In fact, it is not grinding, but it works like a grinding wheel. This is a simple tool only, but this tool is rotated. And along with its rotation, it is also slided. So once you slide it and you bring it over here, so the wear on the tool surface is less and still you are able to generate this groove. Just assume how you would generate a groove on the side. That groove can be generated by electro discharge grinding process. This electro discharge grinding, when done with wire EDM process, becomes wire micro electro discharge grinding process. And here what you do is you are generating a micro size of tool. Initially, when we had the machine, we did not have tools other than 300 micron size of tungsten. So what we did was we made brass shafts up to 350 microns by micro turning, and then we put up this brass shaft over there, and with this wire, molybdenum wire, I think it was molybdenum or maybe brass, I don't recollect exactly. By moving this, what we did was we started reducing the size of this tool. It was continuously rotated, so it worked on the diameter, and we focused on reducing its diameter. So wire micro electro discharge grinding can be used for that purpose. So this is something about the micro turning, micro milling, and micro electro discharge machining. Of course, the time is reaching 8, but I would request the coordinators to give me about 15 more minutes so that I can give some idea about the nano manufacturing. Now, this is one interesting name, Richard Feynman. If you are not aware about it, you may search it in Google. His lectures, he was a professor of physics. His lectures are recorded and they are available sometime in early 60s. And he was the first person to talk about nanotechnology. Of course, he did not work on nanotechnology, but he gave this thought, he gave this idea. So his intention was he launched some 2-3 problems for for the researchers, for the students to work on, and that is how he moved to a concept of nanotechnology. Till then, nanotechnology was not even in textbooks. He was the first person to give them. He said that there is a possibility that we can store information on very small scale, maybe in the size of the atomic range. We can write with atoms. So if I want to write H, maybe I can put various atoms and write my name. And once that is possible, then we will further miniaturize machines and factories and electronic circuits, and we can work at atomic level. He gave this information and he gave this idea of nanotechnology, but he did not coin this term. He did not define the term nanotechnology. It was a Japanese researcher known as Taniguchi who termed nanotechnology in one of his review paper in 1974. So though the concept of nanotechnology was given by Richard Feynman sometime in early to mid 60s, the term nanotechnology came up in 1974, which was defined by Taniguchi. And Taniguchi he predicted the future of nanotechnology very effectively. This is the reproduction of a graph which he put up in his paper in 1974. And the technological advancements have happened exactly as per this graph. You can see that normal machining at some point of time in 1960, in normal machining, we were able to produce 100 microns. That was possible, normal machining. And this normal machining means I have a machine on which I can easily do it. I don't need to go to clean rooms. I don't need to go to certain specialized laboratories to do it. And this normal machining started getting developed beyond 1960, and you talk about 1920-25, somewhere over here. Now normal machining has reached less than 1 micron. That is a possibility. You have lapping processes, you have finishing processes. You can easily buy it even from JAM. These machines are available and you are able to do it. These are being used for mechanical comparators, micrometers, and dial gauges. If you see how we define precision machining means your target is to work with the repetition of half micron. So in somewhere in 1940s or 1950s, that range was somewhere around 100 microns. And we reached somewhere close to nanometers in 2025. This is being done. If you reached, say, 2000, in 2000, 1 micron was possible. In the year 2000, 1 micron was possible. This has gone exactly as how Taniguchi had defined in 74. And maybe in 2060, we may no longer use normal machining or precision machining, because normal machining itself is better than the high precision machining of 60s. So slowly and slowly we are reaching, and nano processing is being attempted right now within the range of 1 nanometers. That is what is being attempted at present day technological capabilities. So what nanotechnology is? Nano manufacturing is something which comes beyond nanotechnology, but nanotechnology is related to the philosophy. It is related to research. It is related to technological development, wherein we try to work at atomic or molecular level, and the size is within 1 to 100 nanometers. The US government defined that way. Japanese have come up with their own definition of nano technology. But basically the thing is, it is that art, it is that philosophy where we want to do something, where we are focusing on the dimensions ranging from 1 to 100 nanometers. Now, when we focus on dimensions which are less than 1 micron, less than 1 micron means 100 nanometers, 900, 700, 500 nanometers. But when we go below 500 nanometers and focus on 1 to 100 nanometers, chemical properties are totally getting different. The chemical reactions that happen are different, because there, suppose if my size, if my capability of observation is 100 nanometers, then with maybe a magnifying glass, I'm just trying to speculate. My size is 100 nanometers. So I will have a magnifying glass of say 1 or 2 or 5 nanometers. With that magnifying glass, I'll be able to see the electrons now. So the chemical reaction that happens altogether becomes a different level of observation. Similarly, the mechanical properties would go into nano domain, nano composite, nano materials. So the way in which bending would happen, the way in which compression would happen, the way in which shear would happen, the way in which molecules would break, the way in which atoms would be removed, that would be very interesting. So altogether, mechanical properties at nanotechnology level is altogether a different scenario. Optical properties, fluid properties, and thermal properties also take a different scale of their observations. So this becomes an interdisciplinary field. What I'm talking about nanotechnology, where you involve chemistry and physics and biology and all sort of engineering and electronics, and even social science comes into picture because ethics also come into it. Sometimes you are working at those dimensions where you will play with insects, where you will play with microorganisms. So social engineering also comes into it. There are a lot of such applications. Due to constraint of time, I may skip this discussion. But when we want to transit from nanotechnology, that is the philosophy of nano dimension, to actually manufacturing in nano dimension, if we want to transit into it, what work is required to be done? There are no set machines available on large scale which would carry out nano machining, which would carry out nano EDM, which may carry out nano bending, which may carry out nano extrusion. Those machines are not available. People have attempted once or twice, they have tried to demonstrate, but they are still not available on a larger scale. If there is a possibility where somebody is ready to make it, then also that is not economically viable. So this transition is right now going on, and there are two ways which are attempted. One is the top-down approach and the other is bottom-up approach. Two ways of creating nano dimensions. In case of top-down approach, processes like chemical vapor deposition, CVD process, photolithography, physical vapor deposition, wherein you convert the material into vapor and deposit it somewhere and create those features. Here the feature size are produced somewhere close to 100 nanometers. That is being done in laboratories with CVD or PVD or photolithography process. What you do is you have this deposited film. This is the substrate where you want to work on, and then you carry out the photoresist. This is the photolithography process. You have a mask, a virtual mask. You pass certain frequency of light, and then you, wherever it passes, it burns and creates the mask is being etched. And this is where you carry out the process by chemical etching. And now this is available for the next phase of machining, next phase of work, wherein you deposit material and then create pillars of nano dimension. That is top-down approach. X-ray lithography, ion beam lithography, electron beam lithography are being utilized at nanoscale instead of photolithography. Of course, they are under investigation, they are under study, and hopefully within next 10 years or so, because Taniguchi graph defines that this would be possible after around 2040. So in next 10 to 15 years, this should be easily available in market. Bottom-up approach is again another interesting technology. This has been demonstrated by researchers at MIT along with IBM. What they did was they separated atoms. These are atoms. These are not laddus. These are atoms. These are atoms separated from somewhere, and with the help of scanning, tunneling microscope, I suppose, I'm not sure. With that, they attracted the atom and then deposited it somewhere. So one atom was brought from somewhere. Maybe it was here into, it was placed over here. So the way we lift the pen and place it somewhere, one atom was placed, another atom was placed, and this is how atom by atom this is being placed. Just imagine what would be the size of this. It may not be even 1 nanometer. But they deposited this many number of atoms. Of course, they may have tried thousands of times, and it may have happened only one time, because the bond between a single atom and this base would also be very weak. By the time you have put up this, the initial atoms may have already fleed their surface. So you can see they have created I, B, and M out of it. This is bottom-up approach. So now if I deposit 2 more atoms over here and then 1 atom over here, so what you did was you created 1 layer, over it you created 2nd layer and 3rd layer. This is the base of upcoming nano 3D printing. So scanning tunneling microscope, which was basically meant to observe and measure the size, started attracting atoms. So from there, this concept came, and wherein bottom-up approach for nano manufacturing is attempted. So these are the processes which are available, which are being investigated: scanning tunneling microscope for bottom-up approach, and electron beam lithography, X-ray lithography, and ion beam lithography for top-down approach, which are being utilized for creating nano manufacturing. Now, this top-down approach would be similar to machining, whereas bottom-up approach would be a deposition process. It may not be called machining, at least as of now. So these are some of the things which I liked to discuss. And there are 4 different generations for transiting from nanotechnology to nano manufacturing. What we need to do, the first task in R&D is to synthesize and fabricate the passive structures. What structures are required from where and from which nano machining or nano manufacturing may be carried out. That was the first thing. This is being largely done. The second generation involves giving active functionality to nanostructures. So I create a nanostructure, but what would I do with it? I create a nano pillar. What will I do with it? So it should have the flexibility to be operated. Somewhat similar to the hairs that we have on our skin. So those hairs generally do not have any functionality, but they are flexible enough to have different positions. The third generation would be these nanostructures would be combined to develop nanosystems. So multiple nanostructures come together and nanostructures define. This is something which is coming up. And final generation would be integrating heterogeneous molecular nanosystems, especially for biomedical applications, with functions. So you create a system, but it does not function. What you want to do is you want to create a system, and by itself it will do the function also. So largely nano manufacturing would be confined in next 10 to 15 years in biomedical applications. We will be able to treat cancer. Cancer surgeries would be done with nano fabrication and nano manufacturing. Tumors would be removed. Brain surgery would be possible. Heart surgeries would be possible. So that would result into improving the life expectancy of human race. So nano manufacturing, of course, may not have possibility of engineering applications as on date, but right now the biomedical applications are like low-hanging fruits. People are trying to attempt and trying to work on it, and maybe in a couple of years, maybe 5 to 10 years, this should become reality. So this is how I end my discussion. Starting from 1 micron, sorry, 1,000 microns, we are trying to reach 1 nanometers. So that entire scale, what sort of possibilities are available today and what are the future projections? That is what I tried to discuss. Of course, there is a lot more which I can discuss, but maybe I would have been not able to discuss this in a span of 7.5 hours. So thank you very much for the. I assume that this was a patient listening. If you are available on the other side of the screen. But in a way, I'm very much sure that many of you would have benefited, would have attended this. And I suppose that these lectures would also be made available online for others to refer in days to come. Thanks to all the participants and thanks to the organizers for this opportunity. Back to you, Taylor, sir. Thank you.
Yes, sir. Thank you very much. Thank you very much, Dr. Dave, sir. And definitely this, your presentation and whole session will be available online also. And later on the participant and other our youth can take a benefit of it. And I will share that link with all also whenever once we upload this on the public domain.
Perfect.
Okay.
So I suppose that
now
we are already
open.
late, so I'll not. If there are quick questions, we can have some questions. Otherwise,
Yes. Yes, sir. Yes, sir. we are now opening the session for question and answer. If anybody has a question, please show your please raise your hand. Prashant. Prashant, now you can speak.
Sir, good evening, sir.
Yes. Good evening.
Is there such a kind of facility available in Gujarat in any institute, micro machining related?
Micro turning and micro milling facility. Micro milling facility is available with me right now in working condition. And I do have another machine where micro turning and micro EDM is also possible, but that machine is right now under maintenance. So in a couple of months, that should be ready. Yes, but that facility is available with us. Yes.
Okay, sir. Thank you. Thank you.
Okay, thank you, Prashant. Anybody else? Abhishek Gupta.
Yeah, I think Mr. Abhishek has put up some questions in the chat. Minimum chip thickness in micro machining usually, it depends upon what feature you are generating and what size of tool you are using. But it ranges from, there are examples which range from 5 microns to 100 microns. So the research that people have reported has minimum chip thickness. Of course, when you say minimum chip thickness, I mean to say uncut chip thickness. We are not able to measure chip thickness because whatever chip is generated is in powder form. So what we measure is the size of the powder and not the size of the chip. So minimum uncut chip thickness that people attempt is 5 to 100 microns. Does it affect micro machining accuracy? Yes, it affects very much. So it goes with the speed with which you work on it and the amount of cutting force that you may generate. This will also result into variation in the minor variation into cutting forces, which will produce a greater effect on the stiffness of the part if it is micro turning. So yes, the heat will affect. Micro tool life, yes, there are milling cutters which are coated cutters. Usually, the single point cutting tools, I haven't come across the situation where coating is being applied, but there are milling cutters and some drill bits which are coated with certain materials, and it is reported that they improve the tool life. Other tools, yes, ceramic tools are being used. Carbide tools are widely used. The micro size of the end mill cutters or the twist drills that you see, they are largely made from carbides and they are coated. Fine. So this is how I address. Any more questions from any others? So I believe
Is there
so.
any
There are no
questions?
further questions right now.
Yes. Yes, sir. So thank you very much, sir.
My pleasure, sir. Thanks for the
Thank
invitation.
you. Sure. And it is our pleasure that you have given us the valuable time.
My pleasure, sir, for the
Thank you, sir. We will be continue with
being in
same.
touch for this long
Sure.
time of 1.5 hours is also difficult these
Yes,
days.
yes.
So let it be virtual, but it was good interaction, and similarly, it was good to listen initially Joshi sir as well as our principal sir. So that's how we get chance to interact in the virtual world these days. Thank you very much for the opportunity, sir. If you permit, I would like to leave the session now.
Sure, sir. Thank you very much.
Thank you. Thank you very much. Good day to all. Good night.
Good day to you all. Dear participant, I think you have enjoyed the session number 1. Now we are going to start shortly the session number 2.